Have you ever plugged in, say, a new hard drive, or maybe just a USB stick, and just wondered how your Linux system instantly sees it?
Yeah, or how it boots up so smoothly every single time, even with, complex storage underneath.
Exactly. It feels like there's some kind of invisible hand doing all the work,
Yeah.
but there's actually a really fascinating, a pretty intricate process happening behind the scenes.
And today, we're taking a deep dive into exactly that. Hardware detection and preparation in Djere Linux.
Right.
For anyone who manages these systems, these powerful Linux systems, or even if you're just, curious about what's really going on under the hood, getting a handle on this is, it's foundational.
Yeah, absolutely. And our mission for this deep dive is simple. Give you a shortcut to being really well informed. We've dug through the sources, pulled out the most important bits of knowledge, so you'll understand exactly how Linux identifies hardware, how it manages it, configures it, and how you troubleshoot it too.
And this isn't just theory, right? It's about equipping you with insights for, effective system management and real-world problem solving.
Okay, so let's pull back that curtain then.
Yeah.
When you first power on a Linux machine, how does it even begin to figure out what hardware it actually has? It's like the first step in a conversation, isn't it?
It really is. And for anyone working with Linux, getting comfortable with the command line for this stuff is, it's non-negotiable. You need to be able to pull a detailed inventory, instantly.
Yeah, okay, so what are the key tools?
Well, for a quick look at your disks and partitions, lsblk is your friend. Often, you'll use lsblk-f to see file system types and UIDs right there.
IND.
Yeah. If you're looking at specific internal bits, like a graphics card or maybe a network adapter, lsbc is essential.
PCI devices, okay.
Exactly. And for anything you plug into a USB port, LSE is your go-to.
Simple enough. So those are the kind of quick hit tools. What if you need like a full system blueprint, something really exhaustive?
Okay. That's when you bring out ilshlo. It gives you this remarkably comprehensive report, pretty much every piece of hardware, CPU, network cards, drivers, the works.
Wow, okay. Sounds like a lot of output.
It can be, yeah. So often you'll just use ilshlo short for a summary or maybe pipe it to grep if you're looking for something specific.
Makes sense.
And for the really low-level stuff, the BIOS-level details, think motherboard model, specifics about your RAM stick's dmesg code is invaluable. It's almost like reading the manufacturing labels directly off the hardware itself.
Okay.
And beyond those inventory tools, dmesg is absolutely critical.
Ah, the kernel log.
Precisely. Think of it as the kernel's real-time diary. Every time hardware talks to the kernel, or if there's an error, especially during boot, it logs an entry there.
So super useful for troubleshooting boot problems.
Invaluable. For spotting issues that maybe stop a full boot or just cause weird behavior later on. And then, of course, we have the virtual file system.
Right. Dev, sys, proc.
Exactly. Dev has the device files. Sys exposes hardware hierarchies via sys. And proc gives you runtime data like proc.puinfo or proc.minfo.
Yeah.
These aren't actual files on disk. They're live windows into the kernel's view of your hardware.
So for someone maybe just starting to peek under the hood, that's where you get that kind of aha moment, right?
Definitely.
You realize you can actually query your own system and see all these connections. It's like getting an insider's view. Sounds like a fantastic way to really understand what's happening.
It absolutely is.
Now, here's where, for me, it gets really clever. Once the hardware is detected, how does Linux keep track of it? Especially, when devices are plugged in or pulled out on the fly.
Right.
How does it manage all that dynamically?
Right, that's the domain of udev, or more specifically, systemd on most modern Linux systems now.
Okay, UDEV.
It's the dynamic device manager. Its job is basically creating, naming, and sometimes removing those device nodes you see in the dev directory.
And how does it know when something happens?
It's genius is how it operates. It's constantly listening for something called kernel events or events.
Events?
Yeah, think of the kernel having super sensitive sensors. You plug in a USB drive, unplug a network cable that triggers a event. It's a signal to udev saying, hey, something just happened.
And UDEV reacts.
udev reacts, typically by creating a device node, like, say, devsdb1 for a partition on a new USB drive.
So it's not just recognizing it once at boot, it's this constant monitoring and adapting.
Exactly. And a really, really critical concept udev handles is persistent naming.
Ah, yes. Because devsd might not always be the same disk, right?
Precisely. By default, those names like devsda, devsdb, they can change between reboots if the disks are detected in a different order. Imagine a script relying on devsd suddenly pointing to your main system drive instead of your backup. Disaster.
Yeah, that sounds bad.
So udev rules, you find them in equative-rules.d, let you use stable attributes. Things like device serial numbers, file system UIDs, even the physical port it's plugged into.
Right, like the devdisk-BI'd or devdisk-BUID paths.
Exactly those. udev uses these rules to assign consistent, persistent names, ensuring your system always references the correct hardware no matter the detection order.
Okay, so how do you interact with udev itself? If you need to, say, reload rules or see what's happening.
You use the udevadm command line tool. Udevadm Monitor is fantastic. It lets you watch those events happening in real time. Highly recommended if you're troubleshooting why a device isn't showing up.
Oh, neat, like a live feed.
Pretty much. UDEV info lets you query details about a specific device. And if you create or change udev rules, you use udevadm control reload rules to apply them without needing a reboot.
Handy.
And systemd also integrates tightly with system itself. You can set up actions like automatically starting a backup script when a specific USB drive is plugged in, all managed through systemd.device units.
Wow. That dynamic system really ensures flexibility, doesn't it?
Yeah.
And scalability, too.
It does.
It makes the hardware experience seamless most of the time, but it also gives you these incredibly powerful tools to troubleshoot when things go wrong.
Yeah.
It's like the silent orchestrator, making sure everything just works together.
That's a good way to put it.
Okay, so udev is like the conductor of this hardware orchestra, making sure everything plays nicely. But for it to be so smart, it must be getting its information from somewhere deep, right? Where does udev actually get all that granular detail about the hardware?
That's where sys comes into play. It's another crucial virtual file system, usually mounted at sys.
Yes, okay.
It provides this hierarchical, structured view of the system's hardware, the drivers, the relationships between devices, all directly from the kernel itself. It's really the kernel's way of exposing every single detail in an organized way.
So it's like a live map of the hardware.
Pretty much. When you browse sys, you find key directories. Like sysblock lists your storage devices. Sysclass groups devices by category, so sysclassnet has your network interfaces.
Right.
Sysdevices actually maps the physical device tree, including PCI and USB devices. Sysbus shows the different buses and what's connected. And sysmodule lists all your loaded kernel modules.
So you can literally walk through your hardware's internal structure just by, like, clanning around in sys. That's amazing.
It really is. And you can use it for practical things, too. Need a network card's MSC address? Just cat sysclass netith address?
Assuming if there's the interface, yeah.
Right. Or check a disk's model name, cat sysblock's data device model. Some entries even let you tweak device parameters on the fly, like adjusting a disk's read-ahead value.
Whoa, okay, so you can actually change things through sys sometimes.
Sometimes, yes.
Yeah.
Cautiously, of course. And this is exactly where sys and udev work together. udev reads all this data from sys to make its decisions, creating device nodes in dev, applying those persistent naming rules we talked about.
Yeah, so sys is the data source, udev is the manager acting on that data.
You got it. And it's important to quickly distinguish sys from procs, which is mounted at proc. While proc has process info and some system-wide runtime data like springinfo or meminfo, sys is specifically focused on the device and driver hierarchy and their attributes.
Okay, that clarifies the difference. It really sounds like sys is the kernel's deep, comprehensive blueprint of the hardware. It gives you incredible insight into how everything connects. This is truly getting under the hood.
Absolutely.
Okay, now that we know how Linux identifies and dynamically manages hardware, let's talk about actually preparing it for use, particularly storage. Once you have the disks recognized, how do sysadmins manage storage to give them maximum flexibility, maybe even after the system's already running? Is there a way to avoid getting locked into fixed partition sizes from day one?
Absolutely. And that's where logical volume management, or LVM, really shines.
LVM, heard a lot about that.
It's essentially an extraction layer that sits on top of your physical storage devices. It allows for incredibly dynamic allocation and, importantly, resizing of storage volumes, often without any downtime.
How does that work? What are the components?
Well, there are three main parts. First, you have physical volumes, or PVs. These are your underlying disks or partitions that you designate for LVM use.
So devsdel1, devsdb, those could become PVs.
Exactly. You initialize them using pvcreate. Then you combine one or more PVs into a volume group, or VG, using VGCreate. Think of the VG as a big, flexible pool of storage.
Okay. Pool of storage.
And from that VG pool, you carve out logical volumes, or LVs, using LVCreate. These LVs function just like traditional partitions. You format them with a file system like X4 or XFS, but they are far more flexible.
Flexible how? Resizing.
Resizing is a key benefit, yes. You
Yeah.
can easily extend an LV using lvextend. Then you just need to resize the file system living on it to use the new space that's resized 2Fs for EPS to 4 or XSS growths for XFS, usually done online.
Wow, online resizing. That's huge. What about shrinking?
Shrinking is possible with lreduce, but it's a bit trickier and riskier. You absolutely must shrink the file system first before shrinking the LV, and usually you need to unmount it and run a file system check, fcseek. So planning ahead to avoid shrinking is generally better.
Good tip. Any other LVM tricks?
Oh, yeah. LVM also supports advanced features like snapshots, creating point-in-time copies of an LV, great for backups, and thin provisioning, where you allocate storage space on demand as data is actually written.
That flexibility sounds incredibly powerful for managing storage over time. But what if your needs go beyond just dynamic sizing? What about combining performance and protection against disk failure? That sounds more like RAID, right?
You're spot on. RAID redundant array of independent disks is precisely about that. Managing storage redundancy, performance, and fault tolerance by combining multiple physical disks into a single logical unit.
Okay, and there are different levels, I know. RAID 0, RAID 1.
Several common levels, yeah, each with different trade-offs you really need to weigh up.
Let's run through the main ones quickly.
Sure. RAID 0 is striping. It splits data across disks for potentially blazing fast performance. But, and this is a big but, there's zero redundancy. If just one disk fails, you lose all the data on the array.
Ouch. So maybe for temporary scratch space, not critical data.
Exactly. Then you have RAID 1, which is mirroring. It duplicates data across two disks. High redundancy, if one fails, the other just takes over. The cost. You only get the capacity of one disk.
Right, half the total space.
Yeah. RAID 5 uses distributed parity. It balances redundancy and performance, needs at least 3 disks, and can survive a single disk failure. Pretty common.
Okay.
RAID 6 is like RAID 5, but with dual parity. It needs at least 4 disks, but can tolerate 2 disk failures simultaneously. Great for larger arrays where the chance of a second failure during a rebuild isn't negligible.
Makes sense for critical data.
Definitely. And finally, RAID 10, sometimes called RAID 1 plus 0. It combines mirroring and striping. You get high redundancy and high performance, but it requires at least 4 disks, and you still only get half the total raw capacity.
A balance of the best, but needs more disks.
Pretty much. And in Linux, we typically manage software RAID using the mdob utility. You use mdob create to build an array, mdob detail to check its status constantly. If a drive fails, you'd use commands like mdob fail, remove, and then add to put in a replacement. The array then rebuilds itself.
And you can watch the rebuild?
Yeah, you can usually monitor the progress in proximdstat. It's also worth remembering that RAID and LVM play very well together. You can create a RAID array, say RAID 1 or RAID 5, and then use that entire array device, like devmd0, as a physical volume for LVM.
Ah, so you get the resilience of RAID and the flexibility of LVM on top.
Exactly. Maximum flexibility and resilience. This really shows how you can design storage that meets pretty diverse needs for capacity, speed, and crucially, data protection.
Okay, so fantastic. You've got your hardware detected, dynamically managed with UDAV using info from CIFS. You've prepared your storage with LVM or RAID or both. But how does it all actually come to life when you press that power button? What about the crucial role of the bootloader in that whole wake-up sequence?
Right, the bootloader. It's the very first piece of software that gets loaded by your system's firmware, whether that's the older BIOS or the newer UEFI.
And its job is?
Its main job is to initialize the kernel and get the operating system started. In the Linux world today, we're mostly talking about GRUB, the Grand Unified Bootloader.
GRUB2, okay.
Its core functions are, well, first, it often presents a boot menu. Lets you choose between different operating systems or maybe different kernel versions if you have several installed.
Right, I've seen that menu.
Then it loads the selected kernel image. That's usually a file called vmlinux something, and also the initial RAM disk, the initrams. Loads them into memory.
Yeah. We'll come back to that.
We will. And finally, GRUB passes control over to the kernel. It just loaded, job done.
So how do you configure GRUB2? I know you're not supposed to edit grub.cfg directly.
That's the key thing. Never edit bootgrub to grub.cfg directly unless you absolutely have to and know exactly why. It's dynamically generated.
Generated from where?
It's built from settings in etc default grub. That's where you set things like the default timeout and scripts located in etc grub.d. When you run grub2-mkconfig-o bootgrub2grub.cfg, or the equivalent command for your distro, it reads those files and generates the final grub.cfg.
Ah, okay, so you edit the source files, then regenerate.
Exactly. And installing grb itself is done with grub2install. You point it at the disk, like devsda, to write the bootloader code to the master boot record, MBR, for BIOS systems, or into the EFI system partition for UEFI systems.
And UEFI has fvboot mgr too, right?
Yeah, on UEFI systems, fvboot of MBR is used to manage the firmware boot entries themselves. There's also a tool called grubby, which is sometimes used, especially by package managers, to modify kernel boot entries without regenerating the whole grub.cfg.
Okay, so the bootloader is that critical first software step. But it's just one step. What's the whole journey look like, from hitting power to getting a login prompt? Sounds like quite an adventure for the system.
It really is. It generally unfolds in distinct stages. First up is the firmware stage. Your BIOS, or UEFI, wakes up, initializes the basic hardware, performs a power-on self-test, post, and then looks for and loads the bootloader, grub2.
Okay, firmware, hands off to grub.
Right. Then the bootloader stage. grub2 takes over, maybe shows you the menu, then loads your chosen kernel, vim-linus, and that important initramps file into RAM.
Okay, kernel and initramps in memory. Now what?
Now, the kernel initialization stage, this is where initramps is absolutely crucial. Think of it as a tiny temporary root file system loaded entirely into RAM.
Why temporary?
Because it contains just the essential drivers needed to access your real root file system, especially if that file system lives on something complex, like an LVM volume or a RAID array, which the kernel itself might not know how to access initially.
Ah, so initramps bridges the gap.
Exactly. The kernel mounts this initramps, runs an init process inside it, which loads those necessary drivers like LVM2 or MDED modules. Sometimes you need to rebuild the initramps using a tool like Dracket if you change storage configurations.
Okay, drivers loaded. Now it can see the real root file system.
Yes. Now the kernel switches root. It pivots from the temporary initramps to your actual root file system on disk. And this kicks off the systemed initialization stage.
System takes over from the kernel.
Well, systemed, running as PID1, span it, takes over managing the rest of the boot process. It reads its configuration, figures out the target state like multi-user.target for a command line or graphical.target for a GUI, and starts launching services, often in parallel to speed things up.
So all the background services start firing up.
Right. And once all the necessary services for the target are running, you finally reach the login stage. The system presents either a text console login prompt or your graphical display manager. Ready for you.
Wow, that's quite a chain of events. Firmware, bootloader, kernel with initramps, systemed, login.
Yep. And understanding that sequence gives you a really comprehensive map for figuring out why your system boots successfully or why it might be getting stuck somewhere along the way and where you need to intervene.
Absolutely invaluable for troubleshooting boot issues. Okay, so even with the best prep, the best configuration, hardware can still have problems. Things fail. So when things inevitably go wrong, what's your toolkit? How do you diagnose and troubleshoot hardware issues in Linux? How do you become that system detective?
Right. Becoming a hardware detective in Linux involves mastering a set of diagnostic tools. You need them to identify issues, troubleshoot, and hopefully resolve problems that affect stability or performance.
Where do you start? Logs.
Always start with the logs. dmesg is your first stop for kernel messages, especially looking back at the boot sequence. Look for anything marked error, warn, or fail. Then, journal.tail.z gives you a detailed view of the system journal, often showing problems with services trying to start or maybe device events that went wrong.
Okay, logs first. Then.
A quick check with lsblk can tell you if a component you expect to be there is actually being detected correctly by the system.
Good sanity check. What about specific areas, like disks?
For disks, smartctl from the smartmon tools package is essential. Running smartctl a devda, or your disk device, checks the disk's internal smart health data. It can often predict failures before they happen.
Proactive diagnostics, nice.
Yeah. You can monitor live disk I/O performance with tools like iostat or SAR to see if a disk is being overworked. For RAID arrays, MDAM Detailed Dev MDX is your go-to for checking the array's health and seeing if any drives are failed or rebuilding.
And if you suspect physical damage.
Tools like BadBlocks can perform a surface scan, though it's slow and stressful on the drive. And fdisk is crucial for checking and repairing file system inconsistencies, which can sometimes result from underlying hardware issues.
Okay, disks covered. What about RAM? Memory issues can be sneaky.
They can. FreeX gives you a quick overview of used and available memory. Dmide code type memory can give you very specific details about the installed RAM modules. But for deep testing, you really need something like memtest86 plus new. You typically run it from a bootable USB or CD before Linux starts, and it stress tests the RAM thoroughly.
Right, takes the OS out of the equation. Network issues.
For network diagnostics, start with ip-linked show to see interface status. ftool if0, replace if0 with your interface name, gives you link speed, duplex settings, and driver info. ftool is S. If0 is great for statistics. Look for high error counts, dropped packets, collisions, things that might indicate a bad cable, port, or NIC.
Useful stats, CPU and temperature, things overheating.
Top, or the more user-friendly HTOP shows CPU usage patterns. To check temperatures, voltages, and fan speeds, you need ELM sensors. After configuring it, just run the sensors command.
Sensors, okay.
And on servers, you often have dedicated management hardware. IPMA lets you query the baseboard management controller, BMC, using IPMI for detailed hardware health reports, temps, fan speeds, power supply status, everything.
Powerful stuff for servers. So what's the overall approach? Just run all the tools?
Haha, not quite. The key is a systematic approach. Correlate data from multiple sources. If the system freezes, check dmesg and journal terrell first. Do you see kernel panics, disk I/O errors? Then maybe run smartTGAL on the disks. Or perhaps run memtest86 plus overnight.
Look for patterns.
Exactly. Always check if there are firmware updates available for your components. Motherboard, BIOS UEFI, RAID controllers, NICs, sometimes bugs are fixed there. And then methodical isolation, swap cables, move a suspect disk to a different port, test RAM modules one by one, try booting with minimal hardware connected.
The process of elimination.
Precisely. And if a disk is failing but still partially readable, tools like Dresq, which is better than plain D for this, can sometimes help recover data by skipping over bad blocks. The whole goal is to equip yourself to be that proactive hardware detective, spotting degradation early and resolving failures efficiently.
That's an incredible deep dive. Seriously comprehensive. We went all the way from the system first seeing hardware with tools like LPSI and losses.
Right, and understanding the kernel logs with dmesg.
Through the dynamic management by UDEV using data from the CIFS file system.
Handling device events, persistent naming,
to preparing sophisticated storage using LVM for flexibility and RAID for resilience.
combining them for the best of both worlds.
Then demystifying that whole boot process firmware, GRUB, Initramps system.
Knowing where things can go wrong at each stage.
And finally, equipping ourselves with that diagnostic toolkit, smartTGAL, memtest86, ftool, sensors to troubleshoot when things break. This knowledge really feels foundational for managing Linux systems effectively.
It really is. So what does this all mean for you, the listener? Considering how much we rely on our systems, understanding these foundational hardware interactions, well, it isn't just about fixing things when they break.
No, it's more than that.
It's about anticipating challenges, designing more resilient systems from the start, and really mastering your digital environment. So maybe a final thought to ponder. After hearing all this, what's one hardware interaction you're now more curious about exploring on your own system?